In this video I am again going to discuss about some elementary important properties of topology. So I am going to start my discussion with the definition of perfect set. Now first question arises, what is the meaning of perfect set? So as usual I am giving the definition here in a formal way. We can consider any particular subset A of a topological space x comma tau, then it will be considered as a perfect set if the derived set of that corresponding subset should be identical to the original subset itself. That means simply you have taken A from x comma tau, this is a subset, find out the derived set of A, that is D of A. If you can show that D of A is equal to A, then you can say A is nothing but a perfect set. Now for example you can also take this one. If we consider 0, 1 semi-open or semi-closed in usual topological space induced over R, then obviously if we consider the derived set of this expression, that will be 0, 1. Now here in general if you consider 0, 1 open interval, semi-open interval, then it is different to that of closed interval 0, 1. But if we choose 0, 1 closed, then derived set is also becoming 0, 1 closed, and consequently you can say in this case derived set of A is equal to A. This definition is satisfied, and hence you can say this is perfect set in R comma tau u. Tau u stands for usual topology. Now depending on this definition we have a very important short question, or better to say a result. A set is perfect if and only if A is closed and has no isolated point. Now it follows from the definition one part, because A is perfect you can see that the derived set of A must be equal to A, where I have also mentioned D of A is the derived set of A. That means take union on either side with respect to A. So left hand side will give you A union D of A, right hand side will give you A union A, but right hand side remain unchanged, so technically we can get A. But as per definition of closure, what can you say this one? This particular portion A union D of A, that is nothing but closure of A, that's why I have written A bar. So A bar is equal to A, and consequently we know this condition will be satisfied only when A must be a closed set. But again D of A is equals to A shows that A is closed, and it means each and every possible limit point must be contained within that set, and that's why we can say but D of A is equals to A shows that every point of A is a limit point of A itself, and hence because every point is behaving like a limit point, so you cannot have any isolated point. So technically you have shown A is closed and it should not have any isolated point. So in order to prove the converse part, let us assume that A is closed in x comma tau and A has no isolated point as usual. So it means all possible points which are not isolated points must be limit points of that set A. So we can write each and every point belonging to A must be a limit point, and hence you can say all possible points of A must be a part of derived set of A, that is A is a subset of D of A. But again we can follow the formal definition of closure. Closure of A, that is equal to A union D of A. Again we know because it is closed, then closure of A and A must be identical, so A union D of A should be equal to A. But from this particular relation you can understand you have taken the union of A and D of A, but ultimately you have shown it is equal to A. So this indicates that D of A is the smaller part, and hence you can say D of A must be a subset of A, and consequently from 1 and 2 we can get D of A is equal to A, but ultimately it is nothing but the definition of perfect set, and consequently you can say whenever A is closed in x comma tau and it has no isolated point, it should be a perfect set. So this is the proof of the first result. Now moving on to the second one, I have given the definition of nowhere dense set. Here you can see a subset of a topological space x comma tau. This is actually x comma tau I have written. It is said to be nowhere dense set if we can show that A bar can have empty interior. A bar can have empty interior means what? If you simply find out the interior of closure of A, then you can show, if you can show it is equal to phi, then you can say definitely the structure is nowhere dense. For example, we can consider the set of integers with respect to usual topology, and we know there does not exist any limit point for z, so interior of z bar must be equal to interior of z, that is equal to phi, and hence you can say it is nowhere dense with respect to R comma tau u. Now with the help of this definition, again I have another important result. A is nowhere dense set. Ultimately it should imply every non-empty open subset of X has a non-empty open subset, disjoint from A. Actually it will be subset disjoint from A. Okay, I am writing this one properly, subset disjoint from A. And also you have to prove the converse. Converse means what? If you can show that there exists some non-empty open subset of X which is satisfying this criteria, that is, it should have a non-empty open subset disjoint from A, then it must be a nowhere dense set. So let us start with the formal definition. A is nowhere dense, that means interior of A bar should be equal to phi. Just take the complementary structure of A bar, then you will see ultimately it will be interior of A complement. We know this is one of the standard results. If possible, we have taken some open subset of X, say that is U. So O intersection A complement bar, as per definition or as per construction better to say, should be not equal to phi. We are choosing this non-empty subset in this way. But already we have used this criteria, A bar complement, that is interior of A complement, so you can replace this one by interior of A complement. If this is not equal to phi, that means you can choose a certain point, say that point is xi. So xi belongs to O as well as xi belongs to interior of A complement, so that you can say xi is a member of interior of A complement. That means xi is itself behaving like an interior point of this structure, so we can consider a suitable neighborhood corresponding to xi, which must contain xi, and also it is contained within interior of A complement. That's why we have this definition, xi belongs to n subset of interior of A complement. Now xi is a member of n. N is nothing but an open neighborhood, that means it is an open set. Also it is a part of interior of A complement, that means n is located within the interior region of A complement, and consequently you can say n is a subset of A complement. So as per our construction, you can say there is nothing common between A and n, because n is a part of A complement. You can imagine if this is the topological space x comma tau, this is one part, say A, this is another part, say C, and say this particular portion is nothing but n, and consequently you can understand n has nothing common with A, so A intersection n should be equal to phi. Now for our convenience, we are defining another structure, say V is equal to O intersection n. Obviously you can understand this is the smaller structure comparison to n, so V is a subset of n, but n is already contained in A complement, so consequently V is also contained in A complement. But V is actually open in X, so if you want to choose any element X taken from V, you should have V intersection A should be equal to phi, because the neighborhood in which V is contained, it has nothing to do with A. That's why V intersection A must be equal to phi. So here you have proved there exists a suitable non-empty open subset of O which is disjoint from A, and consequently you can understand the condition is verified. That means whenever A is nowhere dense, then definitely you have justified the result. Now you have to prove the converse part also. Actually converse part follows from the basic definition. You can go through the formal definition and I hope you can prove it, so that's why I am not showing that one here. So moving on to the next part, but still I am saying if you have any problem to prove the converse part, you can ask me, I will show you the proof. Now moving on to the next part, I am going to consider a topological space x comma tau when it is said to be locally compact. Now here this is an entirely different topic, but still for your examination purpose I have created this video in this fashion. The important things are collected in a separate manner. Now locally compact means what? If it will be locally compact if and only if every point in X should have at least one neighborhood whose closure is also compact. That means initially you are choosing a topological space x comma tau. It is said to be locally compact. The necessary and sufficient condition is that select any point arbitrarily from X, and then if you can justify there exists at least one neighborhood whose closure is compact, then the result will be verified. Now we have a very important short question. Every compact metric space is locally compact. So as usual we can start with this formal definition. X comma D is a metric space which is supposed to be compact. We have to show it is locally compact. Now we know the original space capital X can be assumed as both open and closed. Actually it is a Klopen set. So because of the closedness, X bar is equal to X, and that means each and every point has its own neighborhood, or you can say it is a neighborhood of each of its points. Why? Because it follows from the definition of open set. Whenever you are considering an open set, every point belonging to that open set is behaving like a neighborhood of that point. So technically you can see X contains all possible limit points, so it is definitely closed. And obviously you can say X is compact because it is mentioned in the question. You are going to consider a compact metric space because X is identical to X bar, so automatically you can say X bar is also compact. But what is the property of X bar? You can see because X is open, I have already mentioned it is a neighborhood of each of its points, so X bar will also maintain the same property. That means X bar is compact and in such a way that you can choose any point arbitrarily from X bar. So there exists a suitable neighborhood which is behaving or contained properly within X bar. That means every point, every X bar can behave like a neighborhood of each of its points also. So technically X is definitely locally compact. We have seen the closure of this X is compact, that's why we can say the structure is locally compact. Now moving on to the next one. This is again another important result. Every closed subspace of a locally compact space is locally compact. Now this question comes several times. If you have enough time to prepare this one, I will suggest you definitely memorize this one, obviously after understanding, and this will be helpful for your examination. Maybe it can come in your examination, it can come in your exam. So here X comma tau is a locally compact topological space. Y is as usual a closed subspace of X. Let us select Y belongs to capital Y in an arbitrary fashion. Because capital Y is a part of X, so small y is also a part of capital X. Now as per our definition, because X is locally compact, we can choose a suitable open neighborhood, say N, corresponding to this element Y. But remember the definition, you have to choose this neighborhood in such a way such that its closure must be compact. That means N bar should be compact. Now N as well as capital Y, that means N intersection Y, can behave like an open neighborhood of Y in capital Y. In such a way, closure of this structure should be a subset of N bar. But actually closure represents a closed set, so N intersection Y bar is definitely a closed subset corresponding to the compact subset N. And every subset or subspace of a compact space or compact set is definitely compact. So definitely N intersection Y whole bar, it is also compact. And also it is known to us Y is closed in X, so technically closure of N intersection Y in X is behaving identically just like the closure in Y. That means there is no difference in terms of characteristics of closure. So every point in Y, we can say, has a neighborhood in Y whose closure in Y is definitely compact. So you can consider X is definitely locally compact. So locally compactness, whenever you have to show this one, always remember you have to prove the closure of that compact structure is definitely compact. Now we have a very important criteria, Lindelof space. X comma tau is said to be Lindelof if every open cover of X can have a countable subcover. In compactness chapter during metric space or even in real analysis, we have use this term Lindelof space, or we have also used this definition. Here also to some extent in topological space it is important. Now two different questions can come from this Lindelof space. One, every Lindelof metric space is second countable space, and another theorem is what? Every Lindelof topological space is second countable. The second one is very important. Topological space, Lindelof topological space is second countable. That is very important. So initially I have shown you the proof of every Lindelof metric space is second countable. This is also important, but if you have to choose between these two, I will suggest every Lindelof topological space is second countable. You have to choose this one. So in brief, I am trying to say this one. As usual, we can say a certain metric space X comma D, which is Lindelof. We have to show it is second countable. So correspondingly, we are trying to create an open cover of X. Now open cover means what? Obviously it will be nothing but the cluster of an open set. So these open sets can be considered as a collection of open ball. So you can see I have created certain open balls having center at X with radius 1 by m. Now as per our condition, because the space is Lindelof, it should have a countable subcover. So we can say this particular set G should have a countable subcover. For convenience, I am saying that one is G dash. Intentionally we are using this notation xn m comma 1 by m This can be considered as a countable open base corresponding to G for all possible open subsets of X. Now, X belongs to G be taken arbitrarily. There exists suitable epsilon greater than 0 given, obviously sufficiently small, and let us create an open ball having center at X, epsilon radius, that is Sx comma epsilon is properly contained within G. Now here let us choose a suitable positive integer m0 which is greater than 2 by epsilon. Again I will say initially you need not to memorize this one, later on we will define why we have taken this one. I hope if you have seen the last video of topological spaces, then you will see I have used the same value, and there also I told you not to initially remember this value, later on it will be adjusted automatically. So here we are also doing the same criteria. So here you can see, if possible, this particular structure is behaving like a cover of X, that means X and m0 1 by m0, where m0 is a fixed integer. So definitely corresponding to this m0 we can select a suitable positive integer n0 such that this open ball contains a certain point X. Now if possible there exists another point Y which is distinct from X. Now to find out the distance between X and Y we can have the famous triangle inequality. So distance between X comma X and not m0 plus distance between X and not m0 comma Y. Now here you have obtained two different parts. Now let us consider each of them is less than what? Its radius. So what is the radius? 1 by m0. So both of them are less than 1 by m0. So distance between X and Y is less than what? 2 by m0. Now 2 by m0, this part you have to show must be less than epsilon. So if 2 by m0 is less than epsilon, then automatically you can say 2 by epsilon is less than m0, or in other words m0 should be greater than what? 2 by epsilon. That's why initially we have defined this one, m0 is greater than 2 by epsilon, no other reason is there. So you have shown distance between X and Y is less than epsilon. But from the definition of open set, what does it mean? Y is a part of S of X comma epsilon. So technically you have started from here. Initially you have selected certain point X belonging to this structure, which you have shown is a part of what? S of X comma epsilon. Ultimately it is properly contained within G. Now this implies, or this suggests, that for every possible point like X corresponding to some open set G, we have created a suitable member, say that is G dash. Remember what was G dash? It was the countable subbasis or countable subcover under G, which is properly contained in G and also itself containing X. That means you can say G dash is the required countable open base corresponding to G. That means for every point it is true, and hence you can say definitely X comma D is a second countable space, and this is the proof of this theorem. Now you have next result as like this: X be a second countable space if every non-empty open set G can be expressed as the union of class of Gi. I belongs to index set I. Obviously this is a class of open sets, then G can be expressed as the countable union of all possible Gi's. Now here you can see I have used the index set I. You can also use lambda, and ultimately you have to prove G is nothing but the union of, in fact it is the countable union of all possible Gi's. Now to prove this one, initially let us consider that for each and every small n belonging to capital N, Bn be the collection of some open sets and it will form a countable basis corresponding to X. Now as per our given condition, G can be written as union of Gi. I is taken from capital I, but we know every Gi is open obviously in X, and Bn is nothing but a basis of X. So if you want to select any arbitrary point X in G, because G is the union of Gi, so at least one of them should contain the point X. So I can say definitely for some I belongs to capital I, X is a part of Gi. But again by definition of base we can say there exists a certain member of this family, say simply Bn, I have written this one, such that it can also contains the point X, which is itself contained within Gi. Now how many points you can select in this way? Arbitrarily many points. So x1, x2, x2, x3, in this way you can consider the collection of all such points, but ultimately they are all contained in G. So we can say union of singleton X. That means you have selected one and another point one after another in a sequential manner. X is belonging to G. This is properly contained within the union of Bn, because each and every x is contained in Bn, which is further contained in union of Gi, that is nothing but G itself, and G, as per definition, it itself contained within Bn, union of Bn. But as per our construction, Bn is nothing but a countable basis, and it is itself a subset of countable basis. So Bn, obviously you can see it is contained in some G. This particular structure indicates that, and hence union of Gi is also nothing but a countable union corresponding to all open sets Gi, and hence you can say that G can also be expressed as the union of all different possible countable unions of Gi's. Here you can see I have used another index set, that is In. Previously I have used I, now I have used In. Now this theorem is not so important. If you can do it, you can go through this theorem, otherwise you can skip it. Okay. Now as mentioned earlier, we have a very important result. Every second countable topological space is Lindelof space. Now we can start with the formal definition. Definitely you have to prepare this one for your examination. X comma tau is a second countable space, and says I is any open cover of X. Because X is second countable, you can say it should have a countable base. Say eta be the collection of that countable base, or better to say eta is nothing but the collection of Bn type of elements where n belongs to n, and it is forming the countable base corresponding to X. Because eta is a base of X and Xi contains all elements like Ui, which is supposed to be an open cover, that means every Ui must be open in X. So for each I belonging to capital I, we can say there exists a suitable member Bn, which is a part of what? Eta, and at the same time Bn must be contained within Ui. Now let us select a new set which contains all possible structures where Bn is a subset of Ui is satisfied. So say that set is nothing but S. Now from the index set we can select some suitable index In. Also we can say this result must be true for all n belonging to n. So technically we can say Bn, for convenience or for specification, is a subset of Uin. Now we have to show X is the union of union Uin. So technically everything, whatever you choose, it is definitely contained within X. So union of Uin definitely is a subset of what? X. And also by our construction, X is a member of capital X, small x is an element, but it is also contained within union of Uin. So capital X is also a subset of what? Union of Uin. So technically combining these two, we can say X must be identical to union of Ui, where I belongs to index set I. So you have seen X, this is a part of some countable base Bn, which is further contained within Ui. Obviously this is true for some n. So in general you can write X is a member of Bn, which is a member of a certain member of Ui. Say that certain member is Uin. So you can say, you can collect all possible elements like X, so that you can say singleton X, union of all of them should be equal to the original space capital X, where capital X is the union of Uin, where n is a certain part of what? N is definitely chosen from set of natural numbers which is further contained within S, and thus it implies that it should behave like a Lindelof space. So this is the proof of this result. This theorem is very, very important, and I must say you have to prepare this one for your examination. And finally I have given an example where I have mentioned that definitely space of real numbers is second countable, and consequently it is Lindelof also. However, R induced with lower limit topology, the space RL is not necessarily Lindelof, because you can say, let us consider the lower limit topology which is obtained by considering Xi such that closed interval a comma b. In fact, inside on the right extremity you can see I have written open set. Actually it is semi open or semi closed, you say. So you have the condition a must be less than b, and a comma b, both of them are belonging to R. So we can say this type of lower limit topology is induced on R, and it is generated by this particular structure Xi. Now finally we are going to justify whether RL is second countable or not, and hence whether it is Lindelof or not. So as usual we can select a suitable countable base of RL, say that is given by Bn. Now if you select any arbitrary point x belongs to RL, then definitely we can say a certain semi-open set x comma x plus 1, obviously it is in the form of an interval and also it is open in RL. So let us select a suitable point, say nx, such that this particular x is contained within Bnx, because all the members like Bn, here I have used nx, it indicates it is the part of the neighborhood of n which contains the point x. As per our construction, it is definitely contained within this semi-open interval x comma x plus 1. Now let us try to define a mapping. F maps from RL to N, satisfying the criteria fx is equal to nx. I am not saying this is eta x, it is nx. Now x comma y belongs to R. Suppose they are distinct with the property x less than y. So x belongs to be nx as per our construction, which is a subset of this. Similarly, fy should be equal to ny. This is not eta y, I repeat. So y is also a member of bny, which is a subset of y comma y plus 1. But as per our construction, because x is less than y, so x can never be a part of this interval, because you can easily understand, here you have x, here you have x plus 1. You can imagine this is say y, this is say y plus 1, or even y can be located after x plus 1 also. So one thing is certain, x cannot be a part of this bny. So bnx and bny, these two countable bases are different, consequently nx and ny, they are also different. That means you can say if x not equal to y, then nx not equal to ny. So f must be injective or 1 to 1, and hence you can say R must be countable. But practically it is not possible again, so we are getting a contradiction, and hence from this contradiction only inference can be drawn that RL cannot be second countable space. So I have created a certain video where you can find out certain important results in terms of examination point of view, and I believe if you go through this video properly and if you remember the techniques or the logics behind these theorems, definitely it will be helpful as well as beneficial for you, and also you can implement this one in your examination. Thanks for watching, and also best of luck for the examination.